4 astronauts will hurtle into Earth's atmosphere at 40,000 kilometers per hour, and for the next 30 minutes, no one can save them but physics. Artemis II will send humans farther from Earth than anyone has traveled in over 50 years. But the real test isn't getting to the moon. It's the return, a violent, precisely choreographed plunge through a wall of superheated plasma where the margin between survival and catastrophe is measured in fractions of a degree. Here's exactly what happens during the most dangerous half-hour in modern spaceflight. When Orion separates from its service module roughly 30 minutes before hitting atmosphere, it's closing on Earth at approximately 40,000 kilometers per hour, Mach 32. That's nearly 11 kilometers every single second. For context, the space shuttle re-entered at about 28,000 kilometers per hour. The International Space Station orbits at 20,600. Orion is coming in roughly 40% faster because it's falling from lunar distance, not low Earth orbit. That extra velocity translates into dramatically more kinetic energy. Energy that must be converted into heat and bled away. The last crewed vehicle to endure this punishment was Apollo 17 in December 1972. Over half a century of engineering advancement separates that moment from Artemis II, but the physics is identical and equally unforgiving. Speed is the enemy, and Orion carries more of it than any crewed spacecraft in 50 years. Orion must hit Earth's atmosphere at an entry flight path angle of -5.86 degrees, measured from the local horizontal. Too steep, even by half a degree, and deceleration forces spike beyond what the crew and structure can survive. The capsule could experience over 10 Gs, and aerodynamic heating would overwhelm the heat shield. Too shallow, and Orion skips off the atmosphere like a stone on a pond, sailing back into space with insufficient propellant to attempt another pass. The acceptable corridor is roughly ±1 degree. NASA's guidance computers calculate thousands of trajectory corrections during the coast, home from the moon, firing Orion's reaction control thrusters to thread this needle. By the time the capsule reaches entry interface, defined as 121.9 kilometers altitude, the angle is locked. From that point, there are no second chances. The crew is committed. As Orion slams into the upper atmosphere, air molecules can't get out of the way fast enough. They compress violently, forming a shockwave that heats the gas ahead of the capsule to temperatures approaching 2,800 degrees Celsius, roughly half the surface temperature of the sun. Protecting the crew is the largest heat shield ever built for a spacecraft. 5 meters in diameter, constructed from a material called AV coat. It's an ablative system. It works by intentionally charring and vaporizing, carrying heat away from the capsule as material is shed. The Artemis I uncrewed test flight in December 2022 revealed unexpected charring patterns on the heat shield, with some material loss that engineers did not predict. NASA spent over a year analyzing those results. They concluded the heat shield performed within safety margins, but updated thermal models before clearing Artemis II for flight. Every gram of that shield is now load-bearing trust. Here's where Artemis diverges from Apollo. Instead of plunging straight through the atmosphere in a single blazing arc, Orion uses a technique called skip entry. After the initial plunge, the capsule's lift vector is adjusted so it briefly climbs back to a higher altitude, essentially skipping once off the denser atmosphere like a rock on water, but deliberately. This does two critical things. First, it spreads the total heat load and deceleration over a longer period, keeping peak G-forces on the crew to roughly 4 Gs instead of the 6.8 Gs Apollo astronauts endured. Second, and this is the operational breakthrough, it extends Orion's cross-range capability to roughly 9,600 kilometers compared to Apollo's approximately 44 kilometers. That means NASA can target a single splashdown zone regardless of when Orion arrives at Earth, rather than scattering recovery ships across the Pacific. During the most intense phase of re-entry, the superheated air around Orion ionizes into plasma, a sheath of electrically charged gas that blocks all radio frequencies. Mission Control in Houston loses telemetry. The crew loses voice contact. For approximately 4 minutes, nobody on Earth knows whether the capsule is intact. This communications blackout terrified engineers during Mercury and Gemini. It remains fundamentally unsolvable with current technology because the plasma is a physical barrier to electromagnetic waves. Orion's computers continue navigating autonomously during blackout, adjusting the capsule's lift vector by shifting its center of mass using internal ballast. The crew monitors instruments but cannot intervene meaningfully. Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Jeremy Hansen will sit in their seats, enduring roughly 3 to 4 Gs of deceleration, and wait for physics to release them back into the world of communication. Once Orion decelerates below roughly Mach 1.4 at about 7,600 meters altitude, the parachute sequence begins. And it's a sequence, not a single event. First, 2 drogue chutes deploy to stabilize the still-tumbling capsule and slow it from around 480 kilometers per hour. At approximately 2,500 meters, the drogues are cut away and 3 pilot chutes pull out the main canopies. Each of the 3 main parachutes is 35 meters in diameter, wide enough to drape over a 12-story building. Together, they slow Orion to about 32 kilometers per hour at splashdown. The parachute system endured 18 development drop tests and 8 qualification tests over a decade. A single main chute failure is survivable. The system is designed for 2 out of 3 redundancy, but the choreography must be precise. Deploy too early and aerodynamic forces shred the canopies. Too late, and the ground arrives first. Orion hits the Pacific Ocean off the coast of San Diego at roughly 32 kilometers per hour, hard enough that the crew feels it. The capsule is designed to remain upright, but can right itself if it flips, using inflatable bags at the top of the module. Within minutes, the USS Portland, or a similar amphibious transport dock ship, dispatches rigid hull inflatable boats and Navy divers. The crew remains inside the capsule during the roughly 2-hour recovery operation, a lesson learned from Apollo, when toxic hydrazine fumes posed a hazard during open ocean egress. The entire re-entry from entry interface to splashdown takes approximately 28 minutes. In that time, Orion crosses from the vacuum of space to bobbing in the Pacific, decelerating from 40,000 kilometers per hour to 0. 4 humans will have completed humanity's return to deep space exploration, brought home by engineering precise enough to defy the violence of orbital mechanics.